Hello and welcome to another video. In this video we're going to be working on minimum number of coins for fruits, and it's the third video in the Biweekly Contest 118. And in this problem, you are at a fruit market with different types of exotic fruits, and you're given a one indexed array prices where prices I denotes the number of coins needed to purchase the ith fruit. The fruit market has the following offer. If you purchase the ith fruit at prices I coins, you can get the next I fruits for free. Note that even if you take the fruit J for free, you can still purchase it to receive a new offer. Return the minimum number of coins needed to acquire all the fruits. So in this first example, we have 3 fruits, and basically you can purchase this fruit, and then because this is one indexed, so this is technically at index 1. So if you purchase the first one, then you can get the next I for free. So if you purchase the first one, you can get the second one for free. But really what you want to do is you want to purchase the first one, and then you want to purchase the second one, and then you want to get the third one for free. So the output is 4. And second problem, obviously you can see you're going to want to get this 10 one for free somehow. So what you want to do is you want to purchase this first one, then you can get the second one for free, and then you can purchase the third one. And then you will get the fourth one for free, so you will get 2. So this problem is pretty straightforward, and pretty much all you really need to do is, well, let's actually look at the constraints. So we can see the constraints is 1,000. So right away we can see that like an n squared solution works. And if an n squared solution works, it makes sense to go immediately to something like dp. It's going to be the most common for an n squared solution. And so for an n squared solution, basically what they're saying is if we purchase at index I and it's one index, so really it's going to be like if we're at 0, it's really going to be at 1, so really it's going to be at I, then we can get the next I plus 1 fruit for free. Because this is 0 index, right? So if we purchase at index 0, we can get the next 1 fruit for free. If we purchase at index 1, we can get the next 2 fruit for free, and so on. But they're also saying that even though you can get them for free, you might not want to actually get them for free. You might still want to buy them, kind of like this. And so it's very similar to like house robber, where, you know, if you rob a house, you can't rob the adjacent one. This is basically the same thing, only now it's saying that, you know, you can skip more than 1. So in house robber, you're only skipping 1. Here you can skip more than 1. So let's just write out some fruit, and let's kind of figure out like what we'd want to be doing. And we don't want to make this too big because like this is an n squared solution. Yeah. So let's look at maybe. Actually, let's look at this one. Let's look at this one. This is small enough. So even though these are 0 indexed, we need to figure out a way to, like, this is honestly the tricky part of this problem, is to figure out, like, if we purchase this fruit, because we're going to have an index, how many can we skip and which one should we go to in the next one? And that's pretty much the hard part. So what we want to do is, like, if we purchase this fruit, since this is 0 indexed, it says that they're at 1 index, but our arrays are 0 index. So 1 index, it would be like this, 1, 2, 3, 4. So if we purchase here, we can skip the next 1. Similarly, if we purchase here, we can skip the next 2 and so on. So really the hard part here is to figure out, like, if we purchase some at some index, because we're going to have some index in the array, then where should we go to next? And like which one should we go to next? And so if we purchase this one, we are allowed to skip this one. So we'd want to go over here. So the equation that we are going to need here is if we are at some 0 index, you know, some 0 based index, the one we need to go to next is going to be index plus 1. This is like the end of the range times 2 plus 1. And let's see how this will work. So if we purchase at 0, then, and the reason the plus 1 is because we're going to use a for range loop. So this is going to get canceled out really. So it's really going to be like this. But then we're going to add the 1 because we're going to have it in a for range loop. So it's really going to be like this. So let's take a look at this. So if we purchase at 0, then we get 0 plus 1, which is 1 times 2. So then we will be at index 2. And that's where we want to be, right? We want to skip this one and go over here. But they did say that you might not want to always skip that one, right? Because, like, let's say this was reversed. say this was a 1 and this was a 10. Now if we purchase here, we don't want to skip here and go here, right? We want to actually, like, what would we want to do? We'd want to purchase here, and then we'd actually want to purchase here so we could skip this one. Actually, if we purchase here, we could skip the next 2, because if we purchase at 2, at 1 index 2, we can skip the next 2. So really, the hard part of this problem is figuring out like how to convert 1 index to 0 index and then where to go next. And so pretty much what we need to do is once we purchase at some index, we need to loop. So we can write this down. Once we purchase at some index, we need to loop to all next available locations and then get the lowest cost. Meaning, if we purchase, let's say, at 2, for this one index 2, that means we can skip 3 and 4. But once again, we might not necessarily want to skip 3 and 4, so we're actually going to have to recurse into them, because let's say we had another one. Let's say this was like 100. Then obviously we wouldn't want to skip 3 and 4. We'd want to do something like skip 3, go to 4, buy 4, and then skip this one. So what we need to do is wherever we purchase, we need to loop to every single possible next location and then figure out like what's the minimum cost there. And that's what we're going to do. So our recurrence relation is going to be this to calculate where to go next, right? And this will work anywhere. So like, let's say we purchase at this index. This is going to be 0 indexed. So if we plug that in, we will get here 1 plus 1 times 2. Times 2. So we can go to index 4. And that is correct. So we're going to go to 0 index, index 4. Right, because if we purchase at 2, if we purchase at 1 index 2, that means we can skip 3 and 4. Right? If we purchase at I, we can skip the next I. So we do, this is like the end of where we can go, and then the start of where we can go is just the one right after. So the range we can go is like this, and this is the very last element. So we basically have to recurse into every single one, and then figure out like what gives us the minimum. And you're never going to have a case of, if you have some range of numbers, you're never going to have a range of like where you have like, let's say, some things like 10, 1, 100, or whatever. Let's say this is our range. You're never going to have a case of, actually, let's say it's like this. You're never going to have a case of you're going to recurse somewhere. We can have a bunch of numbers here. It doesn't really matter. So if this is our whole range that we can recurse to, you're never going to have a case of like recursing here, and then from here, you can't go to the next one because it's too small. So you can only buy like some stuff here. And then later on, you're going to want to go here. You're never going to have that. Right? You're always going to have the case of recursing to some number that will let us skip some bigger number, or just skipping that number right away and going to the bigger number. So in the range we're recursing to, we're never going to want to buy more than one item. So we're not going to have that issue of like, you know, recursing to one place, but then we really wanted to buy this one and some other one. That's never going to happen. So that's why we can do this like nice recursion of just basically figure out once we buy a fruit. So the index we're at in our DP is going to be, let's actually write these things down. So base case, index equals, or is out of bounds, right? Then we should just return 0 because there's nothing to buy. Recursive case is just going to be purchase at I, and this is going to be I0 index, and then skip the next I1 indexed indices. We're not skip, but actually it's not going to be skip, it's going to be loop through the next one index indices and figure out which one of these is the minimum. And that's pretty much it. And then our state is just going to be index, where index is going to be where we're at. So whenever we're at some index, we have to purchase. And then we don't need to have a state for like not purchase, because we could just skip it, right? Like if we purchase at this index, there we go, and we want to skip this one, we don't need to like go here. We can just go to the next index, because skipping this index is going to give us a cost of 0. So similar to the house robber, right? If you rob a house, you skip the next one, it's going to be the exact same thing. Just we can loop through more. Instead of going to like the house 2 across, we're going to have to check a bunch, because we might not always want to skip the whole thing, like they showed in this problem, right? Where you you buy something, but you might not necessarily skip the whole thing. And so that's pretty much what we're going to do. So now we can code it up. So we're going to have, and we can do this using memoization. So we're going to set it visited. And we're going to have dp of an index. So if our index is greater than or equal to the length prices, then we can just return 0. And then if index isn't visited, then we can return visited index like a normal DP. And then finally, we need to actually calculate the next location, right? And so this is the weird part because our index is going to be 0 indexed, but our next location is going to, because this problem is 1 indexed, we need to figure out like where that is. So the next location is, like I said, going to be, you take this 0 index, you add 1 to make it 1 indexed, then you multiply by 2, and that's going to be the next, that's going to be how many you could skip. And then you need to add 1 because when we do the for range loop, it's not going to be non-inclusive. It's going to be exclusive, so this will work out fine. So now finally we need to actually loop through from index plus 1 to this next location and see what's the minimum. So we'll just have a result equals infinity and we'll try to minimize it. So we'll say like for I in range. The first index we can go to is index plus 1 and the last index we can go to is next location. So for example, if this was, like I said, we can look at a few of these. If this was 0, if we passed in dp 0, this would give us 1 times 2, so it would give us 2, and it would give us 3, right? And that's where we want to go. So we can't go to 3, but we can go to 2, right? Because we buy at 0, we skip 1, we go to 2. Similarly, if we buy at 2, 0 indexed, what would this give us? This would give us 3 times 2, 6, plus 1, 7. So really, and it's exclusive, so we can go to 6. And does that make sense? So if we buy at 2, 0 index, this would really be 3, right? So we can skip the next 3. So then if we can skip the next 3, that means we can skip 3, 4, 5. So that means we'd want to go to 6, and that will give us the right number. So this is honestly the hardest part of this, is just getting a 0 index array and converting it to 1 index, and the rest of it is just the basic like house robber problem. So once we have this loop of all the indices we can go to, now we just minimize our result. So we'll say minimize this, and then dpi, get our minimum result. And finally, so this is the result of going to all of these, but we also need to factor in the price of the actual item. Because wherever we're at, we always have to buy, right? We're essentially recursing and skipping indices where we don't have to buy. So wherever we are at, we do have to buy. So we'll say visited index equals result plus price is at index, because we have to actually buy that. And finally, we can return visited index. And at the very end, we just return dp0. And we can run that. It should be fine. So let's take a look. And there we go. And you can probably make some slight optimizations, like if your location is like, I guess we could probably do that here. So what we can do is, as a slight optimization, is we can just make our next location be like the minimum of next location and the length of the array, but I don't think it's going to matter too much. But we can do that, I guess. So we can say like next location equals minimum of this whole thing, and then the length of prices. Like that would be fine. That way we're not going too far, but it's not really going to matter. Like in fact, it actually might be slower. Oh, let's see. All right, it needs to be length of prices plus 1. There we go. Oh, there we go. It's actually faster. Okay, cool. Yeah, so essentially what we did basically is like, let's say we were at almost the end of the array. Like, let's say we were here, and we can skip a bunch, but we don't need to recurse into cases that are like way out of bounds. So now this should just work like this. I think. Yeah, so there you go. A slight optimization. You can probably make some small ones there, but it's still going to be basically the same time. So not a big difference. Okay. And so now what we need to do is we need to figure out the time for this. So this is pretty basic, right? We just have an index, which is ov(n), and then we are looping, and for the loop, that's also going to be ov(n), so we have an n-squared solution, which is fine because our constraints were really small. And for the space, it's going to be ov(n) because we just have this one dimension that we're storing. So yeah, I think that's gonna be all for this one. Kind of easy for like a third bi-weekly contest, to be honest. I feel like the second one was a lot or not a lot, but harder. And honestly, the only hard part is, like I said, figuring out how to go from zero index to one index and actually getting these indices correct. This took me a little while. I kept getting like the wrong index. And yeah, that's gonna be all for this one. Hopefully you liked it. If you did, please like the video and subscribe to the channel. And I'll see you in the next one. Thanks for watching.